Hello, it's Scott Manley here, and after a bit of hiatus, I am back with another batch of deep space questions. This is where I'm answering questions from my supporters over at Patreon, which at the moment I'm trying to do some spring cleaning there, put up some new content, but one of the deals is that if you ask questions there, I will eventually try to answer it impromptu and off the cuff in my own, style. And so let's get down to action here. First question is from Tobin Werner, who says, Scott, I'm a huge fan, but I'm new to Patreon. Not sure where to ask the questions. Well, apparently you've put them in the right place. Good job. But I've been thinking and looking at different research done on tidal heating of planets and moons. Would it be applicable, physics/math-wise, to heat Mars or spin the core by towing sufficient mass into orbit, such as a Class C or M, and presumably mean asteroid, a very large TNR using harvested fuel from the asteroid is the only way I can think it would be possible to move a mass in decades of time. So look, there's a couple of questions here that are being asked, right? But first of all, tidal energy generation. Now, if I got my physics right, if you've got an object orbiting another, the tidal heating, it basically goes as the eccentricity squared and the semi-major axis, or 1 over the semi-major axis to the power 6. So it's not like an inverse square. It's an inverse, to the power 6. It's terribly dependent upon distance from the parent body. And really, to get the kind of heating you would need to warm up Mars to make it into like a tectonically active world, you couldn't do that by towing an asteroid into orbit around it. It's simply too small. And if you tried to move it close enough, then it would be inside the Roche limit and it would tear up and form into a ring. You would really have to move Mars into orbit around a large planet like, say, Jupiter, if you were going to heat up something the size of Mars. I mean, the energy just isn't in something small. Now, if you didn't worry about surface features, you could just crash the asteroids into Mars. That would be a lot simpler than trying to insert them into a low, highly eccentric orbit and then somehow not have them break up over time. Now, how you would move them? Well, yeah, you could do the classic example where you take an asteroid and you put rocket engines on it. You could hit it with a kinetic impact or DART style, and I'm sure you can get some amplification that way. Nuclear weapons are always an option, or light sails, those are potentially there. And finally, you can use gravitational impact encounters with other asteroids which you are controlling to perhaps kick these things around. Anyway, look, I don't think heating up Mars by putting something into orbit is viable, but if you don't mind big craters on the surface, you could definitely put some serious energy into the planet by just smashing asteroids into it, preferably comets, because I think they have some more like atmospheric, volatile components. Okay, David Hodge. David Hodge is saying, hello, Scott. Would it be possible for humans to produce a sufficiently large and presumably directed gravitational wave such that it could be detected elsewhere on Earth? Given that gravitational waves travel at high speed and are not obstructed by matter, they seem like an interesting communications medium. However, I suspect the energy requirements are unattainable. Can you humor us by telling us what it would take to pull this off? Okay, so I once read an article where some physicist who was smarter than myself basically figured out how big a gravitational wave detector you would need to detect. I think it was a baseball or something like that being hit by a bat. So to make gravitational waves, you have to take a mass and accelerate it. It's not the velocity, it's the actual acceleration that matters. And a thing getting hit by a baseball bat is comparable. So I think his result was that it was something like 1,000 times the size of a galaxy. You would have to have one of your detection arms if you were going to detect that. Now, you might say, well, what if I had something that weighed 1,000 times the size of a baseball and accelerated it, like, say, a gun shell? Then you would only need something the size of the galaxy because your energy would go up proportional to mass. Sort of, but there's a sort of wrinkle in this because we detect things by the way they stretch space-time. We detect the waves by them moving back and forth and changing space-time. And it's the amplitude that we are detecting, not the energy. So if you know physics, the energy in a wave is proportional to the square of the amplitude. That means if you make something like 100 times more powerful, you only actually increase the amplitude of the wave by a factor of 10. So you would only shrink, so if you increase your energy, your gravitational wave event by a factor of 10,000, then you could shrink your gravitational wave detector down to something the size, 10 times the size of our galaxy. So it's not really practical. And you still have to deal with speed of light and things like that. Yeah, I mean, look, gravitational waves are phenomenally powerful events, right? Some of the early ones that I've read about, they are something like, 30 solar mass black hole, 35 solar mass black hole, like spiraling into each other, generating this chirp, and the final object has 62 solar masses. They've converted 3 solar masses of matter into gravitational energy, and it's barely detectable. Yeah, so we're not doing that. We're not building a communication system like this. Maybe you could put neutron stars in close orbit and then somehow modulate their rotation speed and then have a gravitational wave detector somewhere that could detect this. I'm just not sure how you would modulate the speed of neutron stars in a meaningful way so that you could actually communicate something. It would take some pretty radical forces. Okay, old boy. Scott, could you address the issue of using methane as fuel? It seems obvious to me, since methane is 80% hydrogen, that it's a good choice, but it hasn't been used much until now. Why is that? Well, first of all, it's 80% hydrogen by molecular composition, but only 25% hydrogen by mass. But that's a good thing. Well, I think the reason why most rockets started out using kerosene was simply that's what they had on hand. They had jet fuel, and they knew they could sort of make a rocket fuel version of it rather easily. And I think many of the engineers at the time said, well, liquid oxygen, that adds complexity. We don't need to add even more complexity by using a cryogenic second propellant. If we're going to do that, we might as well go with hydrogen. So I think that is one aspect of it. I think that lighting methane oxygen engines was considered to be slightly more complicated and they had more hard start issues with it. But it's just more that it really got the push in recent years. I think really, I remember methane always being something that was there, but when people started talking about going to Mars and using it as a propellant, that's the sort of generation that came into rocket science and said, why aren't we using methane? And so that's why it's coming everywhere, and also because it actually is significantly cheaper than kerosene, given that most of the impurities that would ruin your day with kerosene just can't simply stay in solution when you've got such a light molecule. I, of course, am completely clueless about this. I'm just giving you my take. Anyhow, Lorenzo von Matterhorn. Is that a real name? That is a pretty awesome or cool made-up name. Anyway, look. Hey, Scott. Raptor 2 has 230 tons of thrust. So does that mean the force is on the inside of the engine bell, and from there it is carried to the rocket itself? I don't get it. I mean, 230 tons! Exclamation mark. Look, okay. Look, here's the thing. Forces in rocketry are pretty big, but you got to understand, your structural materials are exceptionally strong stuff. Like the structural stainless steel that's used in rocket engines has like a tensile strength, and this is more compressive. They have a tensile strength of something like, 500 megapascals, which if you translate it down, that means each square meter cross section of material can support a load of 50,000 tons. So if you want to support 230 tons, that means you need an area about like that size to support the load. Now, you then take a nozzle, and the nozzle is about that size at the throat and gets out much bigger down, and you stretch that area, like 5 centimeters by 5 centimeters by 10 centimeters, stretch it out over the whole nozzle, then that gets to a relatively thin area. it's not such a big deal because you're distributing that material over a relatively large area. So, here's the thing. I think the harder thing with engines is more that you're dealing with this very hot area and it's very high pressure, right? The combustion chamber, 300 atmospheres of pressure. That means on every square meter of the combustion chamber, you have 3,000 tons of pressure. So, like, shrink that down. That means 300 kilograms per square centimeter pushing outwards. I think that's right. Like, it's a fairly substantial force, and you're carrying that on just 1 square centimeter. But it's totally doable with structural materials. The harder part is just that many materials just fail when they get very hot, so you have to figure out the cooling system. Anyway, okay, what have we got next? Nathan! Hi Scott, would it be possible for SpaceX to fly a booster from Boca Chica to Cape Canaveral point to point? Just the booster, no Starship. Maybe SpaceX can continue to manufacture boosters in Texas and get them to Florida under their own power. I guess some type of hat may be in order. Well, okay, so I don't actually know the distance from Boca Chica to Florida, but what I do know, the mass, I think current estimates for the mass of the booster, probably about 200 tons. We know that it carries about 3,600 tons of propellant, so that's like a 19-to-1 ratio in terms of wet to dry mass. And if you do the math with that, you get a delta V of about 9 kilometers per second. That's pretty close to what it takes to get into orbit, so it can definitely lob it the distance that it needs to get to Florida. However, if you're using up that kind of delta V to get the speeds necessary, you're probably going to be hitting the atmosphere at much higher speeds than the super heavy booster would be in a regular launch where it's carrying like a Starship with it. So at that point, if it doesn't have enough propellant left over, it needs to get rid, it's going to hit the atmosphere going very, very fast. And unlike the Starship second stage, it doesn't have this heat protection system. And I don't think it would handle it particularly well. I mean, in particular, look at those big grid fins. Those have very narrow radius of curvature, right? Those things are going to melt if you try to re-enter at, 6 kilometers per second. I don't know exactly how much speed you would hit the atmosphere at if you were going from Boca Chica to Florida, but I'm pretty sure it would be high up there and enough that they might need an entry burn, and if they don't, and that would cut down on the amount of delta V they could commit to launch it up there. So this is something that, again, I need to come back and do some more math on to think that's possible. But I think that the further you throw it, the more likely you are to end up burning up in the atmosphere. That's really just the way it works. Okay, Dave Wynyard. Hi Scott! With the recent launch of the JWST, I wonder if there's ever been a launch escape system designed or attempted for non-living payloads. Of course, it would add cost, mass / complexity for an expensive payload, such as the JWST. I wonder what it would take and whether it might be worth it. And yeah, if there was ever a payload which we might have wanted a launch escape system for, I think the James Webb Space Telescope was definitely up there, being $10 billion worth of, blood, sweat, tears, and government funding to make actually work. Now, I can't think of any case where there's been a launch escape system for an inanimate payload. I certainly think there have been tests involving, capsules which had no crew on board, so that was technically an inanimate payload, but it was a test for something that would have humans on board. So I don't think I've ever seen that happening. Although an interesting data point here would be the space shuttle, which was designed to perform its return to launch, or whatever abort modes it would need to do, whether it was a return to launch site or like an abort transatlantic. It was designed to do that with the cargo in the cargo bay. So technically, the payload bay, whatever, would actually be considered, would have a launch escape system. But it was mostly because the humans were attached to the whole thing and they just had no way of getting rid of that mass. Like The Centaur G, which was supposed to fly as a payload assist module, whatever, for the, they wanted to fly some payloads with a Centaur upper stage and the payload attached to that inside the space shuttle payload bay. And part of the emergency systems would be that during an abort, they would vent all the payload out the side of the space shuttle so that it would land with a lot less mass, because the Centaur G was so heavy it would push the limits of the space shuttle. Okay, Nathan Redberg with the W. Hi Scott, started watching you in 2020. You provided so much entertainment regarding space in that time, not space and time. It was such a great boon of knowledge, I hope it still is. I was curious about Mars rovers and why there has never been a mission to the poles of the planet. Is it to safeguard any potential life there? Additionally, wouldn't it be wise for Mars colonists to take advantage of the water ice at one of the poles? Well, there have been 2 missions to the Mars poles. One was Mars Polar Lander, which famously or less famously failed around the same time as Mars Climate Orbiter. It didn't have any problem with, metric imperial conversion. Instead, I think it deployed its legs, and the bump of the legs deploying tripped some sensor, and it thought that it had landed and turned off its sensor. But later, they built Mars Phoenix. And I think the Phoenix name was certainly a reference to the fact that it included hardware that had flown, or the same kind of instruments that had flown on Mars Polar Lander. And yet it flew to the poles and it landed. It wasn't a rover because it was a mission working on a budget. They dug a little hole in the ground and they found little blocks of something which evaporated over time or sublimated, and they think that might have been water. They did wet science experiments. They had a LiDAR that looked at the clouds. They saw snow coming down. So yes, they have actually been to the poles of Mars, and yes, it does appear that there is water there. The problem is that Mars, that's a very cold place. And during the winter, you do get permanently dark times in the Mars poles. And that's not a great place to have a colony, because then you're going to be dealing with several months where you have no sun and things get very, very cold. So I'm not sure that's the best way to do things. But anyway, yeah, it is a legitimate idea. Von Braun, when he created his plan for the Mars mission, the massive Mars expedition with 10 spacecraft and multiple gliders and everything, they were going to land at the Martian poles using skis, because they thought it was just snow up there, and then they would go to the equator. That obviously never happened, but it's not like Martian poles have never been considered. Okay, Blaze Carey, how much light does the Earth emit due to human activity? Could we look for intelligent technological alien life on exoplanets by looking for similar light emissions? Are there any other activities that humans do that could be detectable? So yeah, look, the amount of light pollution that we produce is very annoying for astronomers, but I don't think it would stand out necessarily compared to the ambient light of the Earth or the Sun. What you're really looking for, if you're looking for a biosignature or a technosignature, is something which is narrow band, something which is a feature that occupies a very narrow part of the spectrum and can be tied to some sort of physical process. And there's a number of physical processes that just don't arise in nature, but we might generate through science. And so if you think about it, LEDs that aren't broadband white LEDs that produce certain bands of red or green or blue, those would actually make decent kind of technosignatures, because you'd get this very bright light in a specific color. So I'm not sure if any colored lights that we see, say on runways, use these narrowband LEDs, but that might be a better signal than the much more broadband signal light that we get from other sources. Obviously, if you're looking for human technosignatures, radio emissions used to be a great thing, but as technology is moving on, a lot of the radiated electromagnetic spectrum is moving into more broadband sources, things because you're trying to put more data into the same bandwidth, and it's becoming less like a narrow frequency range and much more spread spectrum, because that's more efficient use of things. But I think FM radio will be around for a while yet. If you look, digital TV is replacing traditional TV all over the world. So yeah, that's that. Okay, Tesla Rob. Scott, the ISS is in orbit so it can be accessed from Baikonur. Is there an ideal orbit for a station? And I would say that would depend upon your goals, right? There are many ideas that might work. There are ideas to put space stations in polar orbits. That would make a lot of sense. I think one thing that makes the orbit that the International Space Station is in not ideal is that it gets into situations where it spends extended time in daylight, like the sun never sets. Those are times during its orbit, during its year, where it has what's called high beta angle. And that means that basically the station remains in sunlight for a long time, which you might think is great because you've got these solar panels that are getting power, but the flip side of this means that they're getting hot all the time and it's much harder. You have to build better thermal control systems, thermal management systems, because you have to account for these rare times in the year when you're permanently in sunlight. So if you make the inclination low enough that your beta angle never gets high enough to keep it in permanent sunlight, then you can have a more balanced setup. You can cut back on your thermal controls a little. You can perhaps build out more batteries. So I think you need to accommodate the battery situation year round. So it doesn't matter. But having the high beta things means that you need better cooling systems just for that limited time of the year when you're permanently in sunlight. So yeah, I think a lower inclination where that doesn't happen makes sense. Okay, finally, George Hill. Hi Scott, why isn't Orion reusable? Thanks. Well, here's the thing. Orion was supposed to be reusable, and there's nothing to say that it isn't reusable except for the service module, which has to be disposed so that the Orion can come back to Earth. But as of right now, they have ordered like 5 Orions to cover the first 5 Artemis missions. Therefore, there is no plan in there to actually test a reused Orion anytime. And frankly, flights are rare enough that I'm not sure we're ever going to see a reused Orion. There's nothing stopping them. And in fact, Orion as a spacecraft has fewer parts that need replaced than Dragon. Like Dragon and Starliner both use lithium hydroxide canisters that need replaced. I think Orion has a closed cycle life support system, so it doesn't need that. So yeah, I don't know. There's no reason why it shouldn't be reusable, but currently they're spending their money buying new ones. And so with that, I'm going to say thanks for tuning in. Thanks to all my supporters. Here's a whole list of them. Yes, you can watch the list of all my amazing supporters. If you want to support me, go over to Patreon. I promise I'm going to be posting more behind the scenes stuff and more old scripts, photos, whatever. Love you guys. I'm Scott Manley. Fly safe.